So, if a pipe bursts in a nuclear submarine, miles beneath the ocean, you don't exactly look out a window to assess the damage. Right.
No, definitely not. You'd be looking at the dashboard.
Exactly. You look at the dashboard, and today we're doing a deep dive into the dashboard of the modern cloud.
Yeah, it's a really unique look under the hood.
It is. We actually have our hands on a highly specific, highly technical operational blueprint. It's the Supermicro SuperCloud Composer Dashboards User Guide.
Release 3.1.0.
Right. Release 3.1.10, dated April 2026. So pretty cutting edge. And our mission today for you, the listener, is to decode this. It's a 30-page manual, and we want to understand exactly how operators keep these massive disaggregated liquid-cooled data centers from, well, literally melting down.
Yeah, melting down under the strain of just global compute demands. It's a fascinating document because, it forces us to confront the physical reality of cloud infrastructure.
Right, because we always think of the cloud as just like magic Wi-Fi space.
Exactly. But when you look at an interface designed to manage thousands of highly dense, heavily utilized server nodes in real time, you aren't just looking at software. You're looking at a translated representation of heavy metal.
Heavy metal, fiber optics.
PCIe lanes, dielectric cooling fluids, all of it. The SuperCloud Composer, or SCC, it basically acts as the singular pane of glass for a data center operator.
Okay, so let's unpack this. The manual positions the SCC dashboard as an, quote, informational management tool.
Right.
Essentially the command center for day-to-day operations. And it details all these visualization options like pie charts, bar charts, area, line charts, the standard stuff.
The classics.
Yeah. But then it explicitly highlights features like the 3D stacking bar chart. And I really have to push back on the utility of that.
You're not a fan of the 3D charts.
Not at all. I mean, in my experience, rendering a third dimension on a 2D screen, it just distorts the spatial relationships.
Yeah.
If you're in a crisis scenario, right, and hardware is actively failing, a 3D chart just feels like executive eye candy.
Eye candy.
It doesn't feel like a functional diagnostic tool. It's like looking at the dashboard of a modern airplane. You don't need to see every drop of fuel swirling around in 3D. You just need a warning light if a line is leaking.
I get that. It is really easy to dismiss 3D data visualization as superficial. But we have to consider the sheer complexity of the variables being mapped in a 2026 high-density environment.
Okay, how so?
Well, an operator isn't just looking at CPU utilization on a single axis anymore. They are likely correlating physical rack space on the z-axis, power draw on the y-axis.
Oh, I see.
And then thermal load on the x-axis. So a 3D stacking bar actually allows an architect to spot localized hotspots.
Like a physical heat map.
Exactly. So you're looking at a specific quadrant of Rack 12, where the thermal output of the memory modules is suddenly outstripping the localized cooling capacity. It's multivariable telemetry mapped to actual physical space.
Okay, that makes sense if you're looking at the macro topology of the room, like you're mapping the physical thermal envelope. But what happens when you need to isolate just a single failing component?
That's where the search functionality comes in.
Right, because the manual spends a lot of ink on that. It specifically notes that the system applies an A&D condition to all search criteria.
Yes, the A&D condition is crucial.
I assume this means the backend database is heavily indexed for real-time multi-tag queries, right? Rather than just simple, string matching.
It absolutely has to be. I mean, the telemetry data pouring into the SEC is immense. We're talking about event-driven architecture where millions of data points are being ingested every single second.
Millions, wow.
Yeah. So the A&D condition isn't just a UI convenience. It really reflects how the back-end time series database is structured.
Right.
An operator filtering by, say, look, Rack 4 A&D severity. Critical. They're executing a highly optimized query to strip away the noise of 10,000 healthy nodes just to isolate the single failing fan or memory bank.
And this is wild, the manual includes a critical caveat right after that. It states, the search values are displayed based on the security restrictions of the logged-in user.
Yeah, that's a big deal.
Right. Because this isn't just client-side filtering where the UI simply hides data. This implies a deeply integrated role-based access control
RBAC, yeah.
operating right at the API level.
That is a very crucial distinction. In a multi-tenant cloud environment, or even just a highly compartmentalized enterprise architecture, the principle of least privilege is absolute.
Least privilege, meaning you only see what you absolutely need to see to do your job.
Precisely. When the browser makes a GET request to the SEC's REST API, the authentication token doesn't just verify your identity. It defines the cryptographic boundaries of what data can even be queried from the database in the first place.
So it's not even pulling the secret data at all.
Nope. A junior thermal technician querying the API will receive a JSON payload containing only thermal data for their assigned zone.
Okay.
But a senior infrastructure architect running the exact same search query receives the global hardware state. So the dashboard dynamically renders a completely different operational reality depending on the cryptographic token of the user.
That's fascinating. So the UI is fundamentally subjective. It's mathematically bound by your security clearance.
Exactly.
And this philosophy of compartmentalization, it seems to carry over to how the interface itself is physically structured on the screen. The manual divides the dashboard into specific layout concepts called quadrants.
Right, the technology buckets.
Yeah, buckets for node status, analytical tracking, storage allocation, and high availability.
The quadrant design is really a classic triage mechanism. You have to remember, human visual processing can only track so many moving elements simultaneously.
True.
By segmenting telemetry into discrete technological domains, the SCC reduces cognitive load. So if the high availability quadrant flashes a warning, the operator's eye is immediately drawn to the systemic risk rather than getting, bogged down in the granular details of storage allocation.
Right, you don't want to be looking at hard drive space when the whole rack is losing power.
Exactly, it's all about focus.
But to actually interpret what those quadrants are telling us, we need to map the digital dashboard back to the physical hardware.
We do.
The guide leans heavily into the rack server POD health and data center resources quadrants, and it defines these terms in the glossary. Like, a POD is a physical collection of multiple racks.
Right.
And a drawer is a chassis containing multiple systems or appliances. And it mentions tracking compute, switch, and JBOF drawers.
JBOF, yes.
I want to focus on JBOF, assuming you, the listener, have a basic grasp of compute and networking. JBOF stands for just a bunch of flash.
It's a great acronym.
It really is. We are talking about a chassis entirely dedicated to highly dense solid-state NVMe storage. So my question to you is, why separate this into its own dedicated drawer? Why not just keep the storage local to the compute nodes like we used to?
Well, the shift to JBOF architectures is driven almost entirely by the limitations of local storage protocols, and really just the physics of PCI lane allocation.
Okay, break that down for me.
Sure. The glossary specifically references legacy protocols like SAS and SATA. SATA was designed for spinning magnetic platters, old school hard drives.
Right, the ones that actually make noise.
Exactly. And SAN has a single command queue capable of holding 32 commands at a time, as opposed to that to a single queue of 256 commands.
Which sounded like a lot back in the day.
It did. But when you attach modern solid-state flash memory to those legacy controllers, the controller itself becomes a massive bottleneck. The flash memory can retrieve data millions of times faster than the SAS protocol can even request it.
Oh, wow. Right, because NVMe Non-Volatile Memory Express, it completely bypasses those legacy storage controllers entirely, doesn't it?
Yes, it interfaces directly with the CPU's PCI Express bus.
So there's no middleman.
No middleman. NVMe supports 64,000 command queues.
Wait, compared to 256?
Yes. 64,000 command queues, and each queue is capable of holding 64,000 commands simultaneously.
That is an absurd jump in scale.
It's staggering. It is a protocol built specifically for the parallel nature of solid-state architecture. The guide actually notes that typically 4 PCIe lanes are allocated per disk, with PCIe 3.0 achieving 1 gigabit per second per lane.
So 4 gigabits per second per drive.
Exactly. So by consolidating these NVM drives into a dense JBOF drawer, you aggregate immense I/O bandwidth into a single manageable fault domain.
But there is a glaring physical problem here.
Oh, there is.
If I take all my blazing fast NVMe drives and put them in a JBOF drawer over in rack A, and my CPU is sitting in a compute drawer over in rack B, I have just introduced a network switch between the processor and its data.
You have.
And standard TCP/IP networking, taking a packet, pushing it through the OS network stack, wrapping it in Ethernet frames, sending it across a switch, and unpacking it on the other side. That adds massive latency.
It does. It ruins the whole point.
Right. If a CPU has to wait hundreds of microseconds for data, you've completely negated the speed advantage of NVMe. The clock cycles are just bleeding away while the processor is sitting there idling.
And that physical bottleneck is the precise reason Composable Disaggregated Infrastructure, or CDI, required a fundamental rewrite of how data center networks operate.
A total rewrite.
Yes. The manual draws a really stark line between traditional hyperconverged infrastructure, where compute, network, and storage are all trapped in the same physical box,
Right.
and disaggregated infrastructure, where they are physically separated to maximize return on investment.
Let's reframe that return on investment part because maximizing ROI just sounds like marketing speak to me.
Fair enough.
Think of it like this. Traditional hyper-converged infrastructure is like having a dedicated combo meal at a fast food joint. You get a burger, fries, and a drink in one box.
Okay, I like this.
If you're not thirsty, you still had to buy the drink. The capacity is wasted. Disaggregated infrastructure is an a la carte menu. I can order 3 patties, no bun, and a bucket of fries if that's exactly what my workload needs.
That's a highly accurate analogy. In a data center, if a database workload requires massive storage but minimal compute, a hyperconverged node just wastes its really expensive CPU.
Yeah.
But with CDI, the management software dynamically provisions a composed node. It logically binds the exact ratio of compute cores from rack A to the precise terabytes of NVMe storage in rack B.
Which brings us back to the physics problem I brought up. How do rack A and rack B talk fast enough to make that logical binding actually perform like a single physical machine?
They achieve this through NVMe over Fabrics, or NVMeOS.
NVMeOS, okay.
And they utilize RDMA remote direct memory access. The manual explicitly highlights RDMA because it is the absolute linchpin of disaggregation.
Because it skips the network stack.
Exactly. RDMA shatters the traditional OSI networking model. It allows the network adapter to transfer data directly from the memory of one computer into the memory of another.
Bypassing the operating system kernel on both sides.
Completely.
Kernel bypass is huge. I mean, the operating system isn't acting as a traffic cop anymore. There are no context switches between user space and kernel space. The CPU isn't wasting precious cycles processing network headers.
The network interface cards, the NICs, they handle the entire transfer at the hardware level.
Yeah.
And to push this over standard Ethernet infrastructure, they use ROCE.
ROCE?
Yeah, ROCE, RDMA over converged Ethernet.
Got it.
This encapsulation allows the blistering speed of direct memory access to traverse the data center's existing physical switches. When CPU in rack A requests data from a JBOF in rack B via ROCE, the latency is measured in single-digit microseconds.
Single-digit microseconds across a network.
Yes. To the processor, that remote storage feels as fast and responsive as if it were plugged directly into its own local motherboard.
That is mind-blowing. And the SCC Dashboard is the thing orchestrating this entire symphony.
It is.
The manual actually references Redfish and POT-M. Now, Redfish is an industry-standard RESTful API for hardware management, which replaced that archaic IPMI standard, right?
Right.
So the SCC isn't manually configuring hardware with scripts. It's sending JSON payloads over HTTPS to the pod manager, the POT-M, which then dynamically manipulates the bare metal state machines to stitch these composed nodes together in real time.
It is quite literally infrastructure as code manifested in physical heavy metal. But, managing logical floating nodes creates a massive monitoring challenge, which is exactly why the manual dedicates Section 4 to system status and performance monitoring.
Right, because how do we know if these Frankenstein servers are actually working right now?
Exactly. So the SEC tracks power, health, and state. Power and health are pretty binary, or just simple thresholds, but state offers a much deeper look into the operational life cycle of the hardware.
What are the states?
The states are enabled, in test, absent, or offline.
InTest is the one that really caught my attention there.
Oh, yeah?
Yeah, because in a traditional IT environment, a server is either racked and running or it's turned off. It's binary. But in a highly elastic cloud environment, InTest suggests this continuous automated workflow of validation, like it's constantly proving itself.
It has to. Disaggregated infrastructure relies on the absolute reliability of the pooled components. When a new compute drawer is slotted into a rack, or even when a node is just repurposed, it doesn't just boot up and join the pool blindly.
It doesn't just say, I'm here, give me work.
No, not at all. The pod manager likely initiates a pre-boot execution environment, or PXE boot, pulling down a really minimal diagnostic OS.
Okay.
Then the hardware is subjected to rigorous burn-in testing. It's stressing the memory controllers, it's saturating the PCIe lanes, and verifying those RDMA latency thresholds we talked about.
Making sure it can actually hit those single-digit microsecond speeds.
Exactly. Only when it passes these automated validation scripts does its state shift from in-test to enabled.
And the manual hints at how these nodes eventually receive their actual usable operating systems once they are enabled. It mentions fast deploy utilizing an LVM-based ISCSI storage pool and a golden image.
LVM being logical volume management.
Right.
It allows the system to instantly carve out a chunk of storage from that massive JBOF pool we discussed, map it to the compute node via ISC-SI, and clone a perfect, pre-configured golden image of the operating system onto it.
So a bare metal processor can literally go from in-test to soothing live web traffic to you, the listener, in a matter of seconds.
Seconds.
See, here's where it gets really interesting, though. The performance metrics track processor bandwidth, memory bandwidth, and I/O bandwidth. But there is a very specific metric that flags a critical physical reality.
Let me guess. Memory throttled.
Yes, memory throttled %. I want to dissect why memory throttling actually occurs, because it's not just some software bottleneck or a bad line of code. When we talk about throttling in a data center, we are talking about the laws of thermodynamics completely overriding compute demands.
You're entirely right. The relationship between processing power and heat is immutable. You can't cheat physics. The power consumption of a CMOS transistor circuit, which makes up both your processors and your RAM, is roughly proportional to the capacitance, the switching frequency, and the square of the voltage.
Okay, so as you push gigabytes of data through memory modules via RDMA,
the switching frequency hits its absolute maximum.
and to maintain stability at those ultra-high frequencies, the motherboard often has to step up the voltage.
Which exponentially increases the thermal output. Every piece of silicon has a TJ max.
TJ max, the thermal junction maximum.
Yes. This is the absolute highest temperature the silicon die can reach before physical degradation or just instantaneous failure occurs.
It'll just melt.
Literally. So the hardware protects itself. Before it hits TJ max, the microcode intercepts the operation and artificially lowers the clock multiplier. It steps down the voltage and the frequency.
So the thermal output drops, saving the silicon. But from the user's perspective, application performance just falls off a cliff.
It tanks. So the memory throttle metric on the dashboard isn't just a performance indicator. It is a thermodynamic alarm bell.
It tells the operator that the workload isn't constrained by software configuration or network bandwidth anymore. It is physically constrained by the inability to move heat away from the chips fast enough.
Which perfectly sets up Section 5 of the manual.
Yes, the thermal quadrants.
And the highly critical liquid cooling health check.
Right. So the dashboard monitors drawer power, processor power, and memory power, directly correlating those wattage draws to maximum inlet temperature and processor temperature. If a system is throttling, it means the air cooling has failed to maintain the delta T.
The delta T being the temperature difference required to pull heat off the heat sinks.
Exactly.
And in 2026, with the sheer density of JBOF and these advanced compute nodes, forced air is just obsolete.
Fans don't cut it anymore.
They really don't.
Yeah.
The specific heat capacity of air, its ability to absorb and carry away thermal energy, is simply too low. To manage the massive thermal design power, or TDP, of these disaggregated nodes, the architecture has to utilize liquid cooling.
Using CDUs, right?
Yes, cooling distribution units, located directly in rack and in row.
Now, pumping liquid through active, ultra-expensive electronics, it kind of violates the primal instincts of every hardware engineer I know.
Oh, absolutely.
Water and electricity are catastrophic together.
A nightmare scenario.
But the thermodynamic math just demands it. Liquid, especially these specialized dielectric fluids, they can absorb orders of magnitude more heat than air. However, the manual details the immense operational anxiety this creates by outlining something called the CDU leak sensor trap report.
The language surrounding the leak sensors is intensely clinical, yet somehow deeply alarming. The manual provides the exact trap format. Looks like this. Alert CH1 external leak sensor error, followed by a long string of numbers in parentheses. 1.3.6.1.1.30.628.1234.579.
I want to pause on that string of numbers, 1.3.6.1.1.1 byte 30628 and so on. That is an SNMP object identifier, an OID.
It is.
This tells us exactly how the monitoring architecture functions underneath that slick UI. The dashboard isn't just constantly asking the leak sensor, are you leaking? Hey, you're leaking every single second.
Right, because that polling method would saturate the management network.
Exactly, it would introduce unacceptable latency.
Instead, it relies on SNMP traps, which are basically asynchronous event notifications. The sensor just sits there quietly until a physical state change occurs.
Like fluid bridging a conductive trace on a sensor pad.
Yes. The moment that circuit completes, the CDU's management card immediately fires a UDP packet containing that specific OID directly to the SuperCloud Composer.
And that OID acts as a highly specific address, like the 1.3.6.1.4.1 prefix routes it to private enterprise numbers, 30628 is a specific manufacturer identifier for Supermicro, and the trailing digits pinpoint the exact geographic and physical sensor that just triggered.
And then the UI translates that raw numerical string into a massive flashing leak-detected pop-up on the operator screen.
3 exclamation points and all.
Yes, because in that moment, the dashboard has to facilitate an immediate incident response. A leak in a high-density rack isn't just a hardware failure. It is an active, spreading threat to the surrounding infrastructure.
Right, because even if the dielectric fluids are non-conductive initially to prevent immediate short circuits, over time, if they interact with dust or degrade,
They can become conductive.
and then you have a massive fire hazard.
Precisely. So the operator must use the SCC to instantaneously migrate the logical composed nodes off the affected physical hardware.
Basically draining the compute workloads away from the rack before they cut the main power to stop the pumps. And when a massive failure like that occurs, when workloads are migrated in milliseconds, power is cut, physical drawers are yanked out of racks, the resulting chaos has to require an ironclad audit trail, right?
It does.
How do you reconstruct the timeline of a critical failure after the fact? That brings us to Section 6 of the manual, which covers accountability through the activity timeline quadrant.
The activity timeline is basically the immutable ledger of the data center. It captures the standard footprints of every single API call, every hardware state change, and every user interaction.
But there is a very specific UI behavior noted in the guide that reveals how data center operatives actually perceive time. It says, if the event time is more than 48 hours, then the system displays timestamp in MMDD format.
Month and day.
Yeah. The shift from highly granular time, minutes and milliseconds, to a broad date format after exactly 48 hours, that's a brilliant piece of UI engineering because it reflects the life cycle of an incident.
It reflects the life cycle, but it also reflects the underlying storage mechanisms of the telemetry data. The SCC is likely built on top of a highly performant time series database, like Prometheus, or maybe a customized variant of it.
Okay.
Storing millions of data points with millisecond precision consumes massive amounts of expensive, high-speed storage. So time series databases utilize downsampling.
Ah, so the UI is actually reflecting the database tiering.
Ex-
For the first 48 hours, the data lives in the hot tier. If an operator is debugging a split-brain failover scenario that happened an hour ago, they need to know the exact millisecond a network link dropped compared to when the standby node attempted to seize the primary IP address.
High resolution time is critical for that tactical forensics work.
But once that 48-hour window closes...
The operational value of that millisecond precision basically drops to zero.
Right. If you haven't fixed it in 2 days, knowing the millisecond it broke doesn't help you anymore.
Exactly. So the database downsamples the telemetry, aggregating the data points to save space, and moves it to a cold storage tier. And the UI automatically adjusts its formatting to reflect this architectural shift.
It transitions from an active tactical display into just an archival compliance log.
Yep. The manual provides some examples of these logged activities too. Things like admin update account or ATA-based create task by external service.
And a particularly destructive example, admin update rack, successfully deleted PDU.
Successfully deleted PDU. Deleting a power distribution unit from the management plane is a highly significant event.
Yeah, to say the least. Because the PDU isn't just a dumb power strip, right?
No, it is an intelligent, network-attached appliance. It monitors voltage loads and actually controls power to individual rack units. If an admin inadvertently deletes the PDU configuration via the API, the SCC loses total visibility into the power state of that entire rack.
And in a high availability or HA environment, losing visibility is often treated exactly the same as a total physical failure.
It assumes the worst.
The management software might assume the rack is dead and initiate a massive automated failover cascade. The activity timeline prevents the resulting outage from being a complete mystery.
Right. When the senior engineers autopsy the failure the next day, the timeline provides the undeniable root cause.
Human error.
Human error. Always a classic.
Which really brings us to the ultimate synthesis of this entire 30-page user guide. The manual defines high availability as, quote, redundant copies of resources that could be quickly, transparently replaced when failures arise.
The critical word in that definition being transparently.
Exactly. We've spent this entire deep dive looking at how operators manage the chaos, the thermal throttling, the RDMA kernel bypasses, the terrifying liquid leak sensor traps, the accidental PDU deletions. It is an incredibly volatile physical environment.
Almost violently so.
Yet to the outside world, none of this volatility even exists.
And that's the point. The ultimate success of the SuperCloud Composer and the entire architecture it governs is measured purely by its own invisibility.
Right.
When a thermal sensor flags a critical TJ max threshold and a processor is literally threatening to melt, the SCC dynamically provisions a new composed node on the other side of the building, migrates the workload over the ROC network in milliseconds, and spins down the overheating hardware.
And every time you, the listener, load a web page, stream a 4K movie, or save a file, a dashboard, just like the SuperCloud Composer, is tracking the power, thermals, and physical liquid keeping that data alive. And you experience absolutely zero interruption.
The system absorbs the hardware failure, reroutes the reality of the data center, and maintains the perfect illusion of infinite, unbroken compute power.
So what does this all mean? The command center absorbs the pressure so the submarine never feels the crush of the ocean. The goal of this incredibly complex software isn't just to fix problems, it's to hide them so perfectly that the end user never even knows a server burned out or a leak occurred. The ultimate success of the cloud is its own invisibility.